So so in a sense, PQ squared is E, right? So you can put it another way. That means that the order of a transposition is 2. Okay, follow that? The order of a transposition is 2. Okay, so this is just E. So E to the A equals E to the B. In other words, A is B. All right, so we've proved that it is injective. So injective, done. Okay, now surjective. How to prove that? Let's see. Now, how do you prove something is surjective? Remember, surjective means that every element in your codomain is mapped to. It might be mapped to many to one, like 2 to 1, but every element is mapped to. There are no, what's the word? Strangers? No. Stragglers? There are no isolated, unmapped elements. No isolated elements. All right, and to show that, for a given, I don't know, what do we call it? Let's say that's element M, and it's any element of your codomain here. So if we can find a corresponding member in this is the domains, the codomain. If an arbitrary member of your codomain, if you can find a corresponding member of your domain that maps to it, in the general case, if given this, you can find the corresponding, if this is the image, right? Remember that the element that gets mapped to. So if that's the image is M. If you can find an element in the domain that maps to it, then, and since that's general, every element will get mapped to. So let's try and find that element in general form that maps to M. Maps to M. So let's try M would be 1, 2 of X, because we're going to use this. So let X be 1, 2 of M. Right? Now why did I choose that? Well, because then f of x, which is equal to this, so there's your transposition of x, right? But x is this, so you get 1, 2, again 1, 2 of m. Alright? So now these, just E, that's just E, like talking about before, so it's just E of m, which is m. Okay? So for an arbitrary member M of a codomain, if you let this one here be the transposition 1, 2 of M, then that one will map to that one. So for no matter what this is, there will be a corresponding element here that belongs to the domain that maps to that. Now, does it make sense? Now, does it make sense? M is a member of the codomain, the target set. And the target set is B, the set of all odd permutations. So M is an odd permutation. So if that is an odd permutation, you add one, you've got one more transposition, so that will make this, then the whole thing will then be even. So you're mapping an even transposition, an even permutation into an odd permutation. So that makes sense. Alright, so so for any element here, M, this one, transposition 1, 2 of M, is the element that gives you that under this general mapping. Okay, so we found it. So for any element here, there's its corresponding element that gets mapped from. Okay, so we've shown that every element here gets mapped to. Therefore, all the elements in the codomain are mapped to, and therefore this function is, by definition, it is surjective, right? So surjective, done. Okay, so we proved it surjective, we proved it injective, and therefore, by definition, this mapping F is bijective. Okay. Now, if it's bijective, remember, it just means one-to-one. So we proved it's bijective. So here, here's your A of n. That's your alternating set, if you like, and we're mapping everything one-to-one into the set B. Okay, so we can now label this B to the n, right? Because it's one-to-one, and it's surjective. There are no what's the word? Singles. There are no unmapped points in here. It's one-to-one. Okay. All right. So whatever A of n equals, because it's one-to-one, it B, the size of B. So the size of B is the same as A of n. Now let's see. S of n is A of n plus B, right? What is this? And think in terms of sets. This is the set of all permutations. This is the set of all even permutations. This is the set of all odd permutations. And these two sets are totally disjoint. They have no element in common. A permutation is either even or odd. It's one or the other. Okay? So, and now they're both positive. Right? So if I mod both sides, so the size of this will be the size of that plus the size of this. They're positive. We're just talking, how many elements? It's not a negative. You can't be negative. It's just the number of elements. All right. So that's true. All right. Now we have this. Okay. So we can put this in. So S of n is just 2 of, we just do this twice. Okay, so that means the size of your alternating set is a half of the size of the symmetric set, symmetric group. Like, okay, now what is the size of this? It's n factorial, right? How many possible permutations do you have of n objects? Well, you've got n factorial. That's how many. And therefore, the size from here, right here. So therefore, the size of A to the n. Now it's a group, so we can talk about its order of a group as distinct from the order of an element. Always that damn confusion. Right? So the size of the alternating group will be half the order of the symmetric group, which is half of this, and this is the size of the symmetric group. So this is just n factorial. So the order of group, the order of the group A of n, the alternating group, is n factorial over 2, which is what you're asked to prove. Hence show that the number of elements in A to the n is half n factorial. Right, important result. And since the order of B is the same as, well, I can't say order, the size of this set is equal to the order of the alternating group. Therefore, the number of odd permutations equals the number of even permutations. And that's quite an important result for future group theory work. Right? So, okay, that's it. The next lecture will be on dihedral groups. Now, what's that? If you hear anything with the word like, or the phrase di or bi, you know it's got something to do with two of something. And hedral, adjective of like face. So dihedral groups are about the symmetry groups of polygons, basically, where when you flip the face, like the way you flip a coin, it's two-faced. So, for example, you had an equilateral triangle, and sort of like that, and you flip it that way, you get the same. The triangle looks the same. And if you get a square and you flip it, that way or this way, or diagonally that way or that way, right, for a square, and so on. So if you get a pentagon, 1, 2, 3, 4, 5 sides, what are the symmetry operations of, say, the pentagon or a hexagon or whatever? And so the discussion of the groups of symmetry operations of these regular polygons, and what I mean by that is the length of each side on these polygons, many-sided polygon, many sides, the groups of the symmetry operations of these regular polygons, that's the topic of the next chapter on dihedral groups, like two sides. So I'll see you then. Ciao.